Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal. Welcome to the fourth clip. In the third clip, we have discussed metriizability of topological spaces, and we get introduced with a new concept called Lebesgue number associated with an open cover of a metric space. And we have seen Lebesgue number for open covers may or may not exist. And for this we have considered two examples. One is this x is the set consisting of 1/2, 1/3, so on, excluding 0, and we have considered the metric dxy equal to mod of x minus y for all xy in x, and we have seen that in this metric space every singleton subset is open, that is, it is discrete in nature. We have then considered an open cover consisting of all those singleton open sets. Okay, and we have taken any delta greater than 0, and by some way we have seen this delta cannot be a Lebesgue number for this open cover. Since delta is arbitrary, we said that there is no Lebesgue number for this open cover. Then we have considered another example, R with standard metric d dxy equal to mod of x minus y for all xy in R. Okay, and this actually produces the usual topology on R. Okay, where open intervals are basic open sets, that is, every open set union of open intervals, and we know in this case every open balls b d x epsilon is open interval of the form x minus epsilon, x plus epsilon, and also every open interval ab is an open ball bd a plus b by 2, b minus a by 2, this. Okay, fine. So in this metric space we see that open balls are open intervals. Okay, so open sets are union of open balls, that is union of open intervals, so it will give the usual topology on R. So R with usual topology is metriizable, and this D is a suitable metric on R. Okay, fine. We have then considered an open cover script C of the form this standard, n to n plus 2, n in Z. Okay, then we have seen this is an open cover of this R with standard metric. Okay, and we have shown that any number delta strictly greater than 0 or lesser or equal to 1 can play the role of Lebesgue number for this open cover. Now you may be thinking wrongly that every open cover of this metric space has Lebesgue number, but this is not the case. If we consider another open cover script C prime for the same metric space R with standard metric like this, where script C prime consisting of this kind of open interval n to n plus 1, n in Z, obviously they will not cover whole R, because 0, then 1, then 2, then 3, minus 1, minus 2, minus 3. If we put n equal to 0, we will get this open interval, okay, which not covers 0 and 1. If we put n equal to 1, we will get 1 to 2, it is also not covering 1. Okay, so if we put n gradually, then this 1 will remain uncovered. In this way you can check that this script this portion, this family of open cover cannot cover whole R. This all the integral points will remain uncovered. That's why I am considering a few more open sets together with this, like this. So open interval n minus 1 by mod n plus 1 to n plus 1 by mod n plus 1. This kind of open interval I am considering n in z again. So they will cover the integral parts. Okay, if you put n equal to 0, we will get minus 1 to 1. Okay, we will get minus 1 to 1. So 0 is covered. If you put n equal to 1, then 1 minus half, that is this 1 minus half to 1 plus half, that is this. Okay, if you put n equal to 2, so 2 minus 1 third, this 2 plus 1 third. If you put 3, you get this. I am plotting all this because, just wait and follow me. If we put now n equal to minus 1, then what we will get? Minus 1 minus half. Minus 1 minus half. That is this. Minus 1 plus half, like this. If we put n equal to minus 2, then minus 2 minus half. Minus 2 minus 1 third. This minus 2 plus 1 third. This in this way. Here we see that while putting n equal to 0, we are getting minus 1 1. While putting n equal to 1, we are getting half to 1 and half. While putting minus 1, we are getting minus 1 minus half. Okay, this 2 minus 1 plus half. So the open intervals from this part generated for n equal to 0 1 minus 1. Okay, if we keep aside for the time being these 3, then we see that all other members of this part of this C prime are disjoint. Okay, so the point that I will use here, if we take n greater than 1, okay, then also the members here are disjoint. Mind it, remember it. Okay, fine. So this is an open cover of the same metric space Rd. Okay, where we have seen this open cover has a Lebesgue number. My claim is this is an open cover. This is not a claim. I have proved this is open cover of Rd. My claim is this open cover, for this open cover there is no Lebesgue number. Okay, so for this let us consider any delta greater than 0. Okay, then there exists a natural number capital N, so that 1 by this capital N strictly less than delta by 2. There is 2 by n less than delta. Fine. Now let us construct this set by the help of this capital N just obtained via delta. So let us take A, B, n plus 1 minus 1 by n, and n plus 1 plus 1 by n. This being an open interval, its diameter is just this minus this. So diameter of A is 2 by n, and it is strictly less than delta. Okay, now this is a subset of R having diameter less than delta, but we will not find a member of script C prime containing this A. Why? Because it has two parts. First part I will show A is not contained in any member of this part of script C prime, and in the second part I will show that A cannot be a subset of a member of this. Okay, so for the time being here, let n, choose n. Okay, there exists n this such that n is strictly greater than 1. I will use the fact this decision. Okay, I can choose strictly greater than 1. If it is not greater than 1, I can take any another integer which is greater than 1, because in this case it will be more less than this, so this. Okay, if we now take larger n, for that larger n, 1 by that larger n will be also less than delta by 2, so I can take it. Intentionally I can take n greater than 1. Okay, fine, because still it will happen. If one get such a natural number, I can impose another condition n greater than 1, then also one can get a natural number satisfying both this as well as this. Very easy. Fine. Fine. Now A cannot be contained in a member like this n to n plus 1, because this n to n plus 1 does not contain any integer. 0, 1, 2, 3, 1, 2. No integer in between them, but it contains an integer n plus 1. N plus 1 minus something, n plus 1 plus something. So this contains an integer. So this contains an integer, but no member like n plus 1 contains an integer. So this A cannot be a member of this. Okay. Okay, now A contained in n plus 1 for no n in Z. Fine, because A contains an integer n plus 1, but none of this n2 n plus 1 contains integer. Fine. Now second case. It is also obvious that since capital N is greater than 1, okay, capital N is greater than 1, okay, I can argue in this simple way that fine, use this inequality for this n. For this n, we can write n plus 1 minus 1 by n, okay, less than n plus 1 minus 1 by n plus 1 plus 1. This is larger than this. This is smaller than this. So smaller quantity has been subtracted. Okay, so it will be bigger. This and this less than n plus 1 plus 1 by n plus 1. It is obvious because minus plus. And this is less than n plus 1 plus 1 by n. Because this is now larger than this. So larger quantity is added to the same n plus 1. Okay. So here we see that the open interval whose left end is this and right end is this is contained in the open interval whose left end is this and right end is this. But this is nothing but our A. Okay, so we can write that then A contains this element n plus 1 minus 1 by n plus 1 plus 1. Since n is greater than 1, so this is positive, so we can write a modulus of this. Similarly, this is n plus 1 plus 1 by mod n plus 1 plus 1. This. And this is a member of this part, no? Of script C. So this is a member of this. Okay, since n n plus 1 is contained in this, okay, and A also contains n plus 1, fine, so done. Now, so A is not contained A cannot be equal to this because strictly less than, no. So A cannot contain this. A cannot be contained within this. Okay, fine. And so A cannot be contained within the others because n is greater than 1 and others are disjoint from this. Okay, if A is contained in some other, so it will be contained within them, but it will contradict the fact that they are this and that one disjoint. Okay, so A neither contained in this nor contained in other member like this or the from this. Okay, so A is not contained in any member of script C prime. So considering any delta greater than 0, we are getting a subset of R having diameter less than delta, which is not contained in a member of script C prime. So this delta cannot be a Lebesgue number for this script C prime. Okay, delta is arbitrary, so this script C prime, this open cover, has no Lebesgue number. Okay, so if we confine ourselves within a particular metric space Rd, then some open cover of it may have Lebesgue number, but some other open cover of the same metric space may not have Lebesgue number. So now the question is under what condition every open cover of a metric space will have a Lebesgue number. A very big question. Okay, under what condition every open cover of a metric space will have Lebesgue number? Okay, so the result is related this question. Okay, this will answer this question, that every open cover of a sequentially compact metric space has a Lebesgue number. Okay, every open cover of a sequentially compact metric space has a Lebesgue number. So existence of Lebesgue number for an open cover not only depends on the open cover, it depends on the underlying space, the character of the underlying space, and this result tells us if the underlying space is sequentially compact, then every open cover, whatever it may be, every open cover of this sequentially compact metric space will have a Lebesgue number. So let's prove this result. Okay, and as in general case for me, I will sketch the proof. Okay, so let XD be a sequentially compact metric space and script C be any open cover of it. Fine. Okay, I will prove it by contradiction. So if possible, let this script C has no Lebesgue number. That is, whatever a positive quantity we consider, it will fail to be a Lebesgue number of this open cover. So if we take 1, it will not be a Lebesgue number for this. If we take half, it will not be a Lebesgue number. If we take 1/3, in general, if we take 1 by n, it will not be a Lebesgue number of this, because it has no Lebesgue number. Fine. So for every natural number small n, okay, 1 by n is not a Lebesgue number. 1 by n is not a Lebesgue number means 1 by n is not a Lebesgue number means there exists a subset of the metric space XD whose diameter is less than 1 by n, but it is not contained in a member of script C. Okay, so for every n there exists a subset. Say Cn of x, okay, such that its diameter dCn is less than 1 by n in general. Okay, but this Cn is not contained in a member of this open cover script C. Okay, and it holds for every n mandate, for every n. Okay, good. Now take a point from Cn, call it xn. So take xn from Cn for all n and n. So from C1 we are taking x1, then C2 we are taking x2. In this way we will get a sequence in x. Okay. So then this xn is a sequence. This sequence in the metric space HD, which is sequentially compact. Okay, fine. So this being a sequence in a sequentially compact metric space, so it has a convergence subsequence. Okay, so let xnk this be a convergent subsequence of xn. Okay, and let this xnk converges to small x in capital X. Okay, now script C, this script C, an open cover of the metric space XD. So script C covers whole X, so it will cover small x, that is script C has a member that contains X. Okay, script C being an open cover of whole metric space HD, then there exists a member O in script C which will contain X such that small x in O. Fine. So O being a member of this open cover, so this is open set. So this is an open set in a metric space containing this X. So we'll get an open ball centered at X having some radius, say epsilon greater than 0, which is totally contained in O. Okay, we define open set in a metric space in this way by the help of open balls. Okay, so there exists epsilon greater than 0 such that the open ball BD centered at X having radius this epsilon is totally contained in O. Okay, this is important. We'll use this. Okay, call it star. Fine. Now let 1 by np is less than epsilon by 2. xnk is a subsequence, so nk is an increasing sequence. If k increases, then nk also increases. Okay, and all nk are integer. Similarly np, so np is an integer such that 1 by np is less than epsilon by 2, and we can do it by considering sufficiently large p. Okay, and for which this np will be sufficiently large enough so that 1 by np becomes less than epsilon by 2. Okay, so let this for some p in n. Okay, now consider x and p. Xn drawn from Cn, Xn drawn from Cn, so Xnp drawn from Cnp, and diameter of Cnp is less than 1 by np. Look at this, diameter of Cn is less than 1 by n. Okay, fine. Okay, done. No? So xnp in Cnp. Okay, now Cnp will be a subset of this open ball BDXNP, centered at XNP having radius epsilon by 2. How it is possible? Because diameter of CNP is less than, okay, so this is CNP, its diameter, it may be the diameter, this is less than 1 by np. Diameter of Cn is less than 1 by n, so diameter of CNP less than 1 by np, and 1 by np less than epsilon by 2. Okay, so this is less than epsilon by 2. Okay, and xnp belongs to CNP, so this is xnp. Now if we consider an open ball having radius epsilon by 2, okay, this is less than epsilon by 2, okay, this is less than 1 by np, and 1 by np less than epsilon by 2, so this is less than epsilon by 2. Fine. So if we consider this open ball, this is centered at xnp, radius epsilon by 2, then this CNP will be contained in this. Okay, fine. Okay, again this subsequence converges to x, and x in this open ball BDX epsilon by 2, BDX epsilon by 2. Okay, So this is open ball, so open set. This is an open set containing X. So open set containing X is this. And Xnk converges to X. Okay, so for this open ball, there exists a natural number say Q such that this Xnk will enter within this open ball bdx epsilon by 2 for all k greater equal to this Q. Okay, so we are getting two integers. One is P and another is Q. Okay, so let M equal to max of these two integers PQ. Okay, so 1 by nm will be less or equal to 1 by np, so less than epsilon by 2, and xnk within this for all k greater equal to m also, both will be true. Okay, fine. Okay, now let Z in C and M. Okay, M max this. Okay, I will show that this C and M contained in O. I will show it. Fine. Wait. I am using this M. So x and k within this for all k greater equal to M. Mind it, because M max of this. Similarly, 1 by nm less than epsilon by 2. Okay, so this will hold for M also. Okay, so x and M will be in C and M. I'm writing this again. So x and M in C and M, okay, is totally in B D X and M epsilon by 2. Okay, and this x and k in bdx epsilon by 2 for all k greater equal to m. That is in particular x and m in bdx epsilon by 2. In particular, x and m in bdx epsilon by 2. Okay, now let Z in CNN. Okay, then what will happen? Then dxz can be written as dx xnm plus dx nm z. Triangle inequality. Now dx xnm look at this xnm within this, so dx xnm will be less than epsilon by 2, so this is less than epsilon by 2 plus Z in CNM, okay, Z in CNM and XNM in CNM, okay. Now Z as well as XNM, right? This both are in CNM, and diameter of this CNM is less than 1 by NM. Okay, fine. Diameter of CNM is less than, or this CNM is totally contained in this. So diameter of CNM will be less or equal to, okay, diameter of this, that the diameter of this is epsilon. This is totally contained in this. Okay, Z and CNM are that. Okay, so DZXNM will be less than 1 by NM. Fine. Now look at this. 1 by NP is less than epsilon by 2. Okay. Now if we put here some larger number greater than this P, okay, like M is larger than P, so NM is larger than NP, so 1 by NM is smaller than 1 by NP, that is smaller than epsilon by 2. Okay, so 1 by NM is smaller than epsilon by 2. Fine, so DZXNM is less than epsilon by 2, so this is also less than epsilon by 2. This is epsilon. Fine. So dxz is less than epsilon. So z in, therefore z in bdx epsilon. And we know by star bdx epsilon contained in O. This is contained in O. So any point Z of CNM is a point of O also. So this CNM is contained in O. And what is O? O is a member of script C. Look at this. There exists O in script C that contains X. So O is a member of script C. So O in script C. But look at the construction of CN. Construction of CN. CN is not contained in a member of script C. Okay, so CNM is not contained in a member of script C, but we are getting the CNM is contained in a member of script C. So this is a contradiction. Okay, so which contradicts the fact that CNM is not contained in a member of script C. Okay, so we arrived at a contradiction. Why we are getting this contradiction? Because we have taken that this script C, this open cover, has no Lebesgue number. So if we consider that this open cover has no Lebesgue number, we arrive at a contradiction. So this open cover must have a Lebesgue number. but this open cover is arbitrarily taken, arbitrary open cover of this matrix space. So we can say that if a matrix space is sequentially compact, then every open cover of it has a Lebesgue number. Okay, fine. So in the next clip we'll get introduced with the another concept, another new concept, okay, which is known as total boundedness. So keep watching. Thank you.